Last keynote speaker is Charles Zhang from Hong Kong University of Science and Technology. He will going to talk about his journey to build a static analyzer for enterprise scale softwares. Please give him a big hand.
Thank you. I'm from Hong Kong University of Science and Technology. I've been working in static analysis for many years. So this is a talk about almost more than 10 years of experience in doing this research, and of course joint work with all my previous and and current PhD students, around 12. So many of them have already graduated and made more money than myself. So outline today is I want to give an overview. So my talk today is very high level. I promise that there are no inference formulas. There's no inference rules. There are no induction formulas. So I'll be mostly talking about an umbrella project that includes many interesting ideas. I want to focus, after the introduction, I'm going to focus on a few key ideas relevant to static analysis, mostly how to do path-sensitive data flow analysis. And then I'll talk about a few future directions of this project. Okay. So this project name is called Clearblue. So it happens later I found out there's another product that has the same name. That if you smile, that means you're still very young and healthy. Okay, no smiles. Good. So since it's a keynote speech, so I have to do something provocative. So I like to open with how to save static analysis. So maybe arguably that's my personal view, but I feel that static analysis is somewhat on the decline in the past few years. Last year we published a paper at ISTA about buffer overflow detection, just to give you some ideas why I feel that way. Sorry. So last year we published ISTA, we won the paper award. Significant work on buffer overflow detection, right? So buffer overflow, this is where the static bug finding started. We found out that where the earlier paper was published 14 years ago. So that's how few people have worked on this in this area. And static analysis was never sort of a mainstream technology, right? It was never on the center stage. It's always sort of a good to have sort of technology. But is there something wrong with this area, with this field? The answer is, of course, no. So let's look at another piece of static analysis technology, which is called X-ray. Right? If you think about it, X-ray is doing static analysis for real-world objects. Here's the inventor. Almost immediately, he invented X-ray at the age of 50, or around my age. He immediately started to get medals from the king, and then he's actually the first Nobel Prize physics winner. All right? So that's how successful static analysis in real life is. Actually, it's very fundamental to many mainstream applications, right? So it's a successful static analysis, a piece of static analysis technology. So I keep wondering that how we can learn from that, right? So the two things that attract me the most is that first, X-ray is very easy to use. In addition for giving a good image of what's inside of you or the objects, it is very easy to use without any intrusive preparation. Right? And also that the output of this technology is just data, it's image. Right? So it doesn't really make any assumption of what your intention is. So would like to, software, of course, nowadays is, I think, is as important as any physical objects, real-world objects, but would also love to have something like X-ray for software, right? And I claim that we don't have it yet. We don't have it. So the input is the software, is software by itself. Right? It's not source code, it's software. It's the software that people use. The output should be the data that describe what the software does. And I claim that that doesn't exist yet. So does that really mean that for static researchers in static analysis, are we really not that smart? Or are we really not working hard enough? The answer is, of course, I can only say for myself, but I work enough, very hard, and I think I'm smart. But I think the reason is because the static analysis is really, really challenging. Okay? This is meant to summarize for people who really have no idea what static analysis is about, but we analyze programs, right? So for this very simple piece of program, when we try to analyze, we focus on the variables, right? These represent the data in the computation. So you look at it very quickly. There are 4 variables in the program. But if you really programming, you think you understand programs, you know that some of the variables actually takes input from other variables as part of the function argument passing. So that will actually produce more possibilities for the values. But if we consider where the function is called, the function can be called multiple times. This is what we refer to as context sensitive. We actually have to double the size of the variables that we need to look at. Okay? So it depends on where the location is, the variables will take different values. Then we take paths into consideration, right? The path means all these if-else branches. If we take those into consideration, we double the number of variables again. Okay. So in relating to X-ray, this sort of describes the granularity of the image, right? So of course, the higher granularity that we'll be able to look at, the better quality of the image we can produce for the behavior of the software. So the important takeaway message here is that we work so hard on static, we're so hard on the algorithm, right? We try to speed it up, right? So we have a cubic for pointer analysis, for example. We have subcubic improvement on the analysis. But don't forget that the base n is already exponential, right? So it doesn't matter how fast your algorithm is, the number of variables to consider is exponential. That's just a physical fact to me. So look at this, this piece of software. This is a Linux kernel, and we are able to pretty accurately compute its call graph. Right, so this is a call graph of 381,000 functions. Right? So if you take this into your picture, combined with this story, it's not because we are not smart enough or not working hard enough. It's just because this is a real monster. Right? It's just so hard to be able to. This is so complicated than any of the physical objects. Right? So that's why X-ray can succeed, but we haven't found it yet for software because it is just so complicated. And there are even more bad news. I work with enterprise a lot. So enterprise means that these are the big software that provide sophisticated ongoing services for many people. okay, such as the Linux kernel. So they're not only big, they're also changing, they're also alive. From Linux kernel, every 6 minutes there is a commit. Okay, so so this is very easy to tally. You can just look at the GitHub data. Of course, as how we develop software is getting more mature, any mature manufacturing actually has more integration than development, right? So you actually purchase software from other vendors. You take open source software and then you put them together, right? So this degree of integration is only gonna get bigger and bigger, right? So, which means that in your software, the software people really going to experience. There's going to have a lot of what I call dark code. Means that the software you have no control of. You don't even know what's inside, right? You purchase them through its compiled form. And also this push of what we call cloud native means that we write these lambdas, right? Lambda programming. We partition our programs into microservices, right? This is how we build for these big scale software. So easy to develop and they're very elastic, right? So, which means that the program that you write as a developer is very small, right? So when you apply your static analyzer, it's going to be very happy. It's going to chew your software for breakfast. But it has nothing to do with the end quality of the whole system, because the whole system is very big and complex. So how to do static analysis in that setting? Of course, also the knowledge we extract from software is more than just finding bugs. We have a lot of other tasks that we need to serve, and often the companies that I work with often require us to solve all of these problems. Otherwise, what's the point of using your tool? So that's really the scary story. Right? So from these observations, here's something that we want to build. I think that sort of behave more like X-ray for real-world objects. Of course, the basic premise is that we need to produce somewhat good quality image. And also, we want to actually produce the image through a non-intrusive imaging. Right? So we don't want to actually interfere with software development cycle too much. Ideally, we would like to scan software from their product form, meaning mostly compiled code by code. And just because of the sheer size of the enterprise software, we have no choice. We have to learn from how people deal with big data. We have to use distributed computing, cloud infrastructure to analyze it. And we have to do incremental analysis. Otherwise, it's impossible to handle the scale. And also, the goal of the static analysis is to produce data, is to produce general forms of data. And we're going to let APIs, DSLs, even LLMs to look at it in any way they like. Okay, so this is something that me and my group been trying to build for the past, let's say, 7-8 years. So the answer to that is the Clearblue project. So here is the architecture of the tool. It's a tool. It's two-chain. So what intake to the two-chain is basically binary. Okay, so any forms of binary or Java bytecode or the machine binary. So our tool is going to. We're not doing decompilation. We're doing lifting. Right? So we're lifting these binaries into. We choose to use LLVM IR. Right? So we're lifting them into IR. And then on top of that, we do a lot of interesting static analysis, such as call graph building, pointer analysis. Lots of type inference because we're lifting from binaries. So there is a precision loss. So after that, we'll produce some kind of graph representation of the behavior. Basically, it's a PDG. Okay, it's a program dependency graph. On top of that, we have a lot of techniques of finding specific bugs. Okay, so these are the papers we published describing different parts of this tool chain. So if you're interested, you can find more details. So this is just what I just described. So what we try to do is we basically try to build whole program PDG. It's not an easy task. And then we store it to disk. We build indices so that we can look up fast. Then we support analysis on demand. So these are the different I just basically just described. I have more details later on, but these are just the different basic steps of how Clearblue works. Okay. So the main technical features of Clearblue is that we basically are good at or focused on doing value flow analysis. Okay, so not the we don't have, for example, a lot of value abstractions. We're handling things like abstract interpretation. We don't focus on that kind of problem. We focus on value flow problems. We're pretty precise, not as of course as ideal as we wish, but we can analyze Linux kernel, for example, 30 million lines of code with 6 layers inlining and full path sensitivity. Okay. We can do asynchronous analysis, means that we are pre-processing these programs and we extract some representation and we store them onto disk. And then we query later. So when you try to find, for example, bugs, you can write queries and extract this data from disk. It's non-intrusive analysis, right? We don't require you to modify any of these your manufacturing process, right? So one painful lesson for any static analysis person is when you try to deploy it in reality, you're going to face with what I call the last mile problem, is that you have to modify how do you extract the symbols, right? So you have to modify the product development cycle of the software company, and which is the last thing they want to do. Okay. So by analyzing binaries directly, we can do it out of a box. So we can support all of the major binary formats, including Java bytecode. So we have some APIs to facilitate very quick definition of value flow queries. Basically, they are just graph traversals. Okay. As a joke, I think you probably hear the joke already, is that everything the PR community is doing is trying to repeat what database people already did. Okay, so well, in our case, it's sort of the same case, right? So this behaves indeed like a database system. So next, I can let's try to be a little bit more technical. So let me talk about some of the essential innovations that we did for inside Clearblue. So again, this is back almost 10 years ago. So originally we we published a paper, PLDI 18, called Pinpoint. So it basically summarized the core techniques that we still use today. Okay. So the main idea is that for enterprise scale software, so some people are going to probably hate me for saying that, but we give up on soundness. So for software of that size, soundness is not that useful because it gives you too much information. All right? So for developers, it was just impossible for us to filter out anything that's really valuable. And for software of that size, precision is impossible to achieve. Right? So how do you know the report of your static analysis result is precise? Unless you give it a POC, right? Unless you give it an input and produce the bug. But how can you analyze all the way to the main function? Sometimes you don't even know where the main function is, right? So precision is impossible to achieve in this setting. So what do? Let's produce something. Okay, let's produce something that's more likely to have some value, right? So which means that we want to have the highest possibility of precision, which is path sensitivity, of course, plus context flow, all these sensitivity fields, right? So all these sensitivities, we want to, in particular, bring path sensitivity into the picture, but with a fixed window, right? So with fixed levels of context. Right? So hopefully we can produce some good results in software of that size. And the core idea is not really, I would think that we actually borrowed a lot of good ideas from existing work. So our focus is to try to address path sensitivity, so borrow from famous work Callisto, that we encode path condition as a Boolean variable directly inside the PDG. So using path condition as a variable, later on I'll have some examples. Use path condition as variables allow us to actually pre-filter a lot of obvious contradictions without really calling set, right? So set is another monster. We do perform pointer analysis, but we're going to do it purely local, right? So intra-procedural pointer analysis. And then we borrow ideas from Saturn to explicitly expose the side effect across the function boundaries, okay? Why do we do that? The end result is that those people who are familiar with conventional value flow analysis, that you can imagine FDS, supergraph, but with pointers all resolved, and with path conditions encoded inside, all right? So that we can do one traversal of reachability query, and then we can collect everything into one query, right? We don't have to do a separate path-sensitive point analysis. We can do everything in one traversal, in one query. Of course, there's the ugly side of it. This is the bottom of the slide. That's why it's very ugly. Is that we have to impose very harsh limits on how we do that. All right, so for example, our inline levels. So the context level we can look at is kept at a number, so usually kept at 6. And since every low stall pairs are gated with path conditions, we have to limit the number of different paths that each low stall pair could be matched within a number, typically 10. So this is the sort of the limitation we impose so that the analysis can actually finish. Okay. So just give you some detailed example of what I just said. All right. So given the program on the left, we have some pointer operations. Right? There's a load and there's a store. Okay. So our first step is to transform this program into another program that would directly expose the side effect of input and output. So the input is a pointer P that's being loaded, which means its content is being accessed. So we actually produce what we call auxiliary variable on the input, which is integer x. Since P, the pointer P is also being stored, which means that we have to produce another variable. So the function, the test doesn't return any value, but in this case, it actually returns a value. And we actually explicitly change this function to return the value, to represent the side effect that's coming from the pointer. So in transforming that, then we transform the caller, which is the main function, so that the result is that everything is purely data flow. Right? We don't have a two-level pointer here. If we have two-level pointer, there will be a sort of the alias that also flows. But after this transformation on the graph on the right side, there are no pointers. Everything is just a data flow. If the data is actual literal integer or float, it will represent the flow of that. If the data is an address, it will represent the flow of pointer. So, so given this graph, we can do on-demand analysis, right? So we want to query if the malloc can flow into the mem copy in the main. We can just identify the source and sink, and try to compute path-sensitive reachability, right? So another feature is that since we represent this path condition using a Boolean variable, we can just use the Boolean variable to represent the path condition. So in a complex graph, there will be interesting results when we abstract actual path conditions, just use Boolean variables. But this is basically what the core idea is. So with this graph, you can do a CFR reachability if you do top-down, or you can do cloning if you do bottom-up. Right? So it's up to you to how to do your search efficiently. But it's purely on demand. There's no pointers to solve. So so this is great. So we can do pointer flow and data flow in one shot. There's no separate stage for doing pointer analysis. So this actually saves a lot of computation. But we hit another bottleneck is because we tried to do path sensitivity. So as you can see, every query involves set. All right. So set is basically becoming a big bottleneck for performance. In this case, we identify that set formulas actually takes up a lot of space. So the process of finding bug for pinpoint was bottom up. So we compute summaries and we actually inline bottom up. But doing that, we found that there's a lot of path conditions that has to be inlined, has to be concatenated. And this actually hurts scalability a lot. So the observation we made in this paper is that we can actually only store path insensitive information, sort of doing a path insensitive inlining. And once we found an interesting path in the value flow for bug finding, we can actually recover all the path conditions from the IR itself, right? So we just look at the LLVM IR, and then we can just retrieve all these path information. when you look back, it sounds very trivial, but somehow people know it's, at year 21, people recognize it's a good idea. Another observation we make is that once we know the program structure, we can actually save a lot of effort in encoding path conditions. For example, when we're encoding path condition for function foo, we have to consider how these variables flow inside function bar and come out, right? So usually we will encode everything with a big formula. A quick look into the function bar is that we found that the input and output has no other path conditions. It's just a linear relationship, right? So there's no use to encode all these linear relationships. So it's equivalent just to ignore whatever's inside and then encode the condition directly without, it would be, so in terms of set, it's the same result, right? It doesn't really affect anything. So by leveraging the program structure, we can actually speed up set a lot. So this is what we did, follow-up work in PLDI 21. The result is, of course, the big saving is on the memory reduction, so we save a lot in storing these path conditions. The memory reduction is quite considerable. There's also follow-up work on that, which is ongoing. So this is unpublished, but I'm happy to talk about it. Is that the earlier work we save space, now we try to save time, right? So how do we save time? Is that in the old IFDS problem solving, basically there are two approaches, right? So one is the CFL reachability, where you from top to down, and then the downside is every time your query changes, your summary has to be recomputed, right? So although you only traverse part of the graph that's relevant. The clone-based solution is interesting. It saves a lot of effort in reusing some of the clones. And if you have multiple source and sink, it can probably also address that as well, because you're doing inlining, you are actually probably looking at, on the way, you can do more discoveries of other source and sinks. But it requires a lot more memory, right, compared to the top-down approach. So we like to combine both. So we like to do reachability. We like to only traverse part of the space that's relevant, but we don't want to actually clone the summaries. But we do clone the summaries, but let's do it in a different way, right? So the difference is we can clone the summaries and we store them on the disk, okay? But we don't just naively clone these summaries. We pre-compute reachability, right? So using CFL grammar and set. So we pre-process these summaries. It's just for value flow purposes, okay? And we store them on the disk. The perceived performance is that when the users are actually using the tool, the perceived performance can be greatly speed up by loading these summaries from a disk instead of actually computing them, right? So we can only look at the sort of the additional lag when we know where the source and sinks are. We just look at the additional lag in their intra-procedural inside their function, and then the rest of the paths can be actually looked up by from a table, right? What table? This table. So this is a quick example. So these different colors represent the entry point and the exit points of these function summaries that we built. So the summaries are similar to the ones that I just talked about before. Then from that, we compute sort of the the value flow paths, right? So for example, there's an entry point to a function. Let's compute all possible paths that can come back, okay? Of course, possible means that they have to set, and they have to have CFL grammar, right? So the sentence is valid on the CFL grammar, and the condition is a set. Okay, so we can pre-compute all these different paths, shortcuts, and just list them on a table, store them on the disk. Okay, and then after a physical query comes, var 1 to var 5, we only need to build up the local connection to the entry points and the exit points of these summaries. And the rest of the paths just can be looked up, right, by the keys to the table. Okay, so basically it's a reachability search for the query and a set check. Of course, this is still somewhat a naive approach. We're still working on making it even more efficient. But as a prototype, it also shows the sort of the benefits, sort of the speeding up. So the overall process is not necessarily shorter because we have to spend a lot of time building these indices. But I think this is the sort of the offline time. As user using the tool, the speed up is dramatic, right? So sometimes it's 200, 300 times faster compared to pinpoint, right? Compared to pinpoint. So this is an interesting, also interesting direction that we're heading. So the last part is, of course, we have a lot of other work that deals with other parts, but I think the most interesting ideas are these ideas. But how can I not? I must do you a very good service by talking about LLM, right? Nobody talk about LLM today. So, I feel like I have to do you a good service by talking about LLM. So how does static analysis, or the conventional notion of the static analysis, interplays with LLM? Okay, so our experience has been that it's pretty good in certain specialized tasks, which we call it boundary problems. So what are the boundary problems? Boundary problems are the problem that the parts of the software that's missing. So there are many different scenarios why they're missing. Of course, they're missing, right? So that's one scenario. The second one is that they're in binary. So recovering from binary is a challenge by itself. Some binaries are heavily obfuscated. Okay, I have also seen other applications that the binaries are dynamically downloaded, so it's just impossible to have. But then there are also limits of static analysis, as well known. For example, the understanding of shapes in the big scale, right? In the big scale, plus loops, right? I.e. recursion. So these things are very hard to analyze. And also because of the size, right? So it's just impossible to be precise. So these are the things that are impossible for static analysis to address, but the users, they don't care, right? So for them, this is their software. They don't care how you do it, but please give me some useful results. I'd like to quickly share three case studies that we use LLM. The first one is alias through containers. That's when shape analysis is impossible for enterprise software. And also, we have some experience in analyzing operating systems. The final case study is LLM versus static analysis. Right? So hopefully they're interesting. So the first case study is data flow through containers. Right? So containers, collections, abstract data structures. So these are things that are very hard for static analysis to get accurate. For example, we can store something into a hash map using a key, and then we can use the same key to retrieve it. Right? When we do that, we know that these two results are the same. And then with that, we can establish a data flow, and then we can proceed analyze a lot of interesting bugs. Otherwise, it's broken. Right? Modern software uses this a lot, so a lot of the paths are broken, which is not good. But is that so hard to analyze for a human? So our intuition is that for certain kind of API pairs that come with the containers, as a human, we can actually quite easy to deduce that certain things are aliases. Right? So for example, push and pop. Right? So when you push something and then you pop, you know that very likely, right? When you push something, you pop immediately. That's a trivial case, but you know that these two things are obvious aliases. Otherwise, it would be very difficult for static analysis to give you that conclusion. But it's very easy for human to deduce that. So what do? We first look at the type signatures. We read the documentation, right? We read the documentation. We read the type signatures, and we read the document. We actually read the sentences, and it's not hard for a human software developer to reach that conclusion. So this is the intuition we had. So these are the two observations. Just quickly skip them. So if we combine them, we ask LLM, and we combine with these type constraints. We combine them together. So let's see, we can make some right conclusions. So this is called so this project is called DA-Infer. It's in the last year FSC. So the result is that it's quite interesting. Right? So these are the things that static analysis, which is no oracle to compare to other than from a sort of subjective judgment, right? The precision and recall are reasonably good, right? So around 80%. Most importantly, we can find additional flows, right? Compared to using the traditional static analysis tools, we can find additional flows. I did another interesting experiment following that. This is not part of the paper, but I told my students that, so this experiment was done in 2023, so let's see if we can do better, right? So we have more powerful AI models now. So let's repeat the experiment, right? Using all these up-to-date, well, maybe not up-to-date anymore, but newer models, and let's repeat the experiment to see what happens, all right? So this, maybe you can ignore the numbers on top, but these are the summary of the accuracies down here, okay? So one interesting discovery is that in this case, DeepSeek is pretty good, but on average, they're pretty much on par, okay? Means that, so for this kind of knowledge, right, so it summarizes the knowledge. Maybe the models, the old models, are already good enough, right? So about knowing something, maybe reasoning model does not really do anything dramatically better than the non-reasoning models. Okay. So this is interesting experiment we did. This is another experiment in detecting bugs in kernel. So the story is that we have, so traditionally when we detect deadlocks, right? So we detect the cycles in nested locking, right? So when we follow the control flow, assuming perfect knowledge, even if a thread does not really acquire locks nested in successive manner, meaning nesting, you could still have nesting with interrupts. Okay, so when a thread acquires a lock, an interrupt can come and grab another one. And then you're going to have deadlock, all right? So, of course, the first job in doing this is to find out where are the interrupts are. So when we process the flow, we have to find out where the interrupts are. What functions represent interrupt handlers? So that's the sort of the task, first task. So naively, we would feed the name of the function to LLM and ask if this is an interrupt handler or not. All right. It turns out that this is a very terrible choice. It has roughly no idea how to answer the question. Right? So 56% accuracy. It turns out that if we can combine static analysis a little bit with LLM, we can dramatically improve this capability. Okay, so the static analysis is very simple. We simply detect a sort of a pattern. So in kernel, interrupt handlers are often registered as a field for some kind of struct that describe a device. So this pattern is really easy to detect, and we find these functions, address taken functions that are being actually passed into these structs. Okay, so this is some very easy static analysis that we can do. After that, we're going to tell LM this is what we found, and please look at this particular function. Okay, so sorry. Yeah, in this example, please look at this particular function to tell me if it's a interrupt handler. And but doing that, we can actually have a lot better performance. Okay, so we can reduce false positives from the naive version of LLM. Okay? We can reduce a lot of false positives. So we can find additional bugs. So this is a very interesting interplay of LLM with the static analyzer. Whereas the previous case was just relying on LLM to find knowledge that static analysis is unable to find. The next little case is about fighting LLM versus Clearblue. So this is what I asked another student try to detect memory wrappers, right? So this is very important for taint analysis, or for value flow analysis, the earlier talk, right? So you have to detect if something is coming out of memory allocation, maybe you need to sanitize on it. Okay, so it's important to detect these memory wrappers, and trust me, memory wrappers are very hard to detect because you just have no idea how people wrap up the memory, the preliminary functions, and how people wrap them up. So the experiments is that we identify, so this is another benchmark, identify 800 kernel functions, 200 wrappers, 200 free wrappers, and 400 non-memory management wrappers. So this is a benchmark, not from us. So we're going to use it to test, to compare the capability of Clearblue versus LM. Okay, so this is the experiment. So we implemented an algorithm for dedicating to find memory wrappers on Clearblue, and we compare that to LLM. So we see who is doing better. Some details about how we do it. So we picked some of the newer models as well. Right. Some details about the prompts that we use. The result is very interesting. So we first prepared the benchmark about 20,000 candidates. So these are the random candidates. But they, so there's no oracle for Linux kernel, right? So, but we try our best to filter out 20,000 wrappers. And inside the 20,000, we're going to see how many of the technique, how many of the wrappers, true wrappers, can be picked out, because we have some oracles, some known facts. So that's the way that we compare. So this is how each model, how many wrappers that each model picked up. Okay, so for example, out of these are there's a sort of man-made benchmark, but each model can pick up a small subset of these wrappers. In terms of quality, we just look at how many. So among the wrappers that picked up, how many of them are in the oracles that we know they are accurate? In this oracle, there's 800 calls. Okay, so that's what we do. So the observation we make here is, surprisingly, LLM model in this task outperforms Clearblue by a very large margin. Okay, so this is what we. In terms of recall, they are roughly equal. Okay. So this is for the right. This is for the allocation wrappers. This is for the free wrappers. This is for the free wrappers. So the LLM models are also on par with the static analysis. So in this way, actually everything is roughly equally good. Okay. So here are some case studies why for some false positives and negatives for this comparison. Right. So this is a case where static analysis failed to find because the call chain is too long, right? So this API is called alloc pages, but involves a very deep call chain. So the Clearblue is not able to figure out the data flow. Another case where LLM fails is that the name of the function doesn't have a little connection with idea of memory allocation. It's called on-register. But basically, on-register, it means that it's going to clean up the memory. In this case, Clearblue is able to figure out the data flow because it's pretty shallow, but LLM cannot. Okay, which is, I think it's predictable. I guess that's all that I want to share in the work that we did. Some takeaways is that static analysis is still a very big challenge. I think not because it's not important, but maybe we have to try to look at some interesting new directions. So there's a need to bring static analysis to product perspective of software. Right? So instead of traditionally it's R&D, it's developer oriented, but maybe we can also look at more on the product perspective. And LLM is surprisingly effective in solving all these specialized occasions. I have no general conclusion, but at least it's better than not having it. in many of these cases, right? There are some future directions. The first direction is to open source it. The reason why we didn't open source is to embarrass the open source. I often found functions of 5,000 lines. But students have very little motivation in actually having a better modularity. I will continue with data-driven static analysis. I think static analysis is also good on having high-level abstractions. A friend in Purdue is doing static analysis on network protocol interactions. This is having great success. In that you can don't have the scale problem. And we're also experimenting with agentic approaches to work with LM to actually produce POCs for the bugs that we find. Okay, so I think that's a more valuable output for the users. I think that's it. Thank you so much. We have a semi-working website that tells more information, but don't trust too much on that.
We have a couple of minutes for questions. So, any question? Oh.
Thank you for your good, very good presentation. I have one question about the memory wrapper identification and how it can be used in scenarios. How can memory wrapper identification be used?
Oh, the wrappers are they act like a disguise of something very important. They look like regular functions, but they're actually very important compared to other functions. So memory wrappers are memory allocators, for example. The variables returned from that is probably worth attention. You might want to sanitize it, or you want to actually, do buffer overflow checks on these targets. Right? So otherwise, you're going to do buffer overflow on any of these variables. But if you know that it comes from a wrapper, then you probably can focus your analysis on that. And also sinks, right? So freeze. If some memory is free, then you probably need to look for, double free or use after free problems.
Also, in a sense that we may focus more on such.
Yeah. We want to know that certain variables represent important information.
Thank you. Thank you for your clarification.
Yeah. Any other questions? So let me ask one question.
So this is maybe a super specific question, but you had this example about trying to detect the deadlocks with the interrupts, right?
Yeah.
So I was wondering what actually the problem was in the example that you showed, because it seemed that there would only be a deadlock if the interrupt in turn was interrupted again.
Yeah, it would be another thread. I didn't show the big picture, but there will be another thread and another interrupt. So they will be forming. So you log 01 and then log 02, the other one log 02 and then interrupt log 01. So
two interrupts.
when the interrupt comes, when the interrupt comes, that the thread has a lower priority, right? So the thread would be suspended, right?
Right,
so
but you would need two interrupts to interrupt each other for the thing to be a problem, or not? Because your handler did the unlock, your interrupt handler, and I guess then then you have another interrupt.
Okay. That could actually form the So if you look, so the problem is look at the program flow. There are no nested locking, but when you consider interrupt, there will be nested locking. So that's that's the problem. But that's not the.
Thank you.
Yeah. Thank you.